Chapter 10, Lesson 1, What is Motion? Can be found on page 282. Our objectives for today are to define distance, speed, and velocity, and to learn how to graph motion while we're calculating speed. When we're graphing motion, we're going to graph motion on a distance and time graph. Let's get into it. Matter and motion. All matter in the universe is constantly in motion, from the revolution of the Earth around the Sun to electrons moving around the nucleus of an atom. Leaves rustle in the wind, lava flows from a volcano, bees move from flower to flower as they gather pollen, blood circulates throughout your body. These are all examples of matter in motion. How can the motion of these different objects be described? Changing position. To describe an object in motion, you must first recognize that the object is in motion. Something is in motion if it is changing position. It could be a fast-moving airplane, a leaf swirling in the wind, or water trickling from a hose. Even your school, attached to Earth, is moving through space. When an object moves from one location to another, it is changing position. So the first question here says, what is in motion? And your answer should be everything. Technically, everything is in motion because even if we sit still on this Earth, the Earth is turning and rotating and orbiting the Sun. Everything is technically in motion, but we're going to describe motion in a specific way in which we're saying that it's changing position. It's going from one place to another. The runners shown in figure 1 here are sprinting from the start line to the finish line. Their position changes, so they are in motion. And the second question says, is there a difference between an object in motion and an object changing position? Well, we wouldn't identify that because an object that is changing position is an object in motion. Here's how we know. Relative motion on the top of page 283. Determining whether something changes position requires a point of reference. An object changes position if it moves relative to a reference point. To visualize the picture yourself, competing in a 100-meter dash. You begin just behind the start line. When you pass the finish line, you are 100 meters from the start line. If a start line is your reference point, then your position is changed by 100 meters relative to that point. Look at figure 2. How can you determine that the dog has been in motion? Well, if he starts out, he's on the left-hand side of the bench where the red ball is, and then he's on the right-hand side, so he's moved based on that reference point. So changing position is all about having a reference point, and an object is in motion if it's changing position. How do you know if an object has changed positions? Our reading check says it's moved if it's moved relative to a reference point. So there's something to say, well, it started here and it finished here, or point A to point B. Changing position, distance, and displacement. Let's find the difference between these two. Suppose you are to meet your friends at the park in 5 minutes. Can you get there in time by walking, or should you ride your bike? To help you decide, you need to know the distance you will travel to get to the park. This distance is the length of the route you will travel from your house to the park. Suppose the distance you traveled from your house to the park was 200 meters. When you get to the park, how will you describe your location? How could you say that your location was 200 meters from your house? However, your final position depends on both the distance you travel and the direction. Did you go 200 meters east or west? To describe your final position exactly, you also would have to tell the direction from your starting point. To do this, you would specify your displacement. Displacement includes the distance between the starting point and ending points and the direction in which you travel. Figure 3 shows the difference between distance and displacement. If you look at the bottom picture, you're showing this movement from where you're starting to where you're going in the park. Notice on the bottom left-hand corner, you've walked across this bottom sidewalk 40 meters and you're moving to the east. So the distance is 40 meters and your displacement is 40 meters, but the displacement has that extra disclaimer of telling you the direction that you're traveling in that reference point. Now in the second block, your distance has changed because you took a left and you walked up the sidewalk. Now your distance is a total of 70 meters because you've gone 40 meters down one way and 30 meters up the sidewalk the other. 40 plus 30 is 70, but your displacement is only 50 meters because of the distance between those 2 points. Displacement is kind of as the crow flies, as they describe it, a straight line from one place to another. Distance, again, is that total measurement, the length of the route that you travel from one location to another. Displacement is the specific direction or the distance between those 2 starting points and ending points. And in the third picture here, it shows that you've walked all the way around this square in the park. Your distance you traveled was 140 meters because you traveled all the way around in that rectangular square, and the displacement is 0 because you're actually back to the starting point. So displacement is always a measure between where you are, where you started, and where you finished, where distance is the total measure of that traveling. On the next page, speed. To describe motion, you usually want to describe how fast something is moving. The faster something is moving, the greater the distance it can travel in a unit of time, such as 1 second or 1 hour. Speed is the distance an object travels in a unit of time. For example, an object with a speed of 5 meters per second can travel 5 meters in 1 second. Speed can be calculated from the equation. Speed equals distance divided by time. And speed is always a measure, it's considered a rate because it is a comparison of two different units. So here you've got distance in meters in the numerator and time, usually in seconds, in the denominator. So when you divide that down, you're going to get a unit of speed in terms of meters per second. Other ways in which speed is calculated uses two different types of measurements as well, where the numerator being distance, like for example miles per hour or kilometers per hour that you would see on the speedometer in a vehicle. The unit for speed is the unit of distance divided by the unit of time. In SI units, speed is measured in units of meters per second. However, speed can be calculated using other units such as kilometers for distance and hours for time. Let's just practice a couple of these in terms of how we would calculate. Number one says, if you traveled 16 meters in 2 seconds, what is your speed? You take the meters divided by the seconds, 16 divided by 2, 8 meters per second. How about number two, 50 meters in 10 seconds, 50 divided by 10 is going to be 5 meters per second. Or 15 divided by 3 is going to be the same. 5 divided by 3, or 15 divided by 3 is going to be 5 meters per second. If you look at the applying math section at the bottom of page 284, it shows you an example of traveling 100 meters in 56 seconds, and then it does the division to say, well, you were going 1.8 meters per second. Let's take a look at the practice problems just below that. Again, I'm on page 284 at the bottom in our practice problems. Number one says, a runner completes a 400-meter race in 43.9 seconds. In a 100-meter race, he finishes in 10.4 seconds. In which race was he running at a faster speed? Well, in order to calculate speed in this example, you're going to have to divide each of these in terms of your distance divided by time and then compare them. So the first one, you've got 400 meters divided by 43.9. You're going to get 9.1 meters per second. In the second example, you've got a 100-meter race. You take 100 and divide by 10.4. You get 9.6. So he's actually running faster in the 400-meter race than in the 100-meter race. Number two, a passenger train travels from Boston to New York. The distance is 350 kilometers in 3.5 hours. What is the speed of the train? 350 divided by 3.5 equals 100 kilometers per hour. So you take that distance, divide by the time, that's how you calculate speed. Now there's two different types of speed when we're talking about the way in which speed is communicated, specifically scientifically. A car traveling in a city traffic might have a speed to speed up or slow down many times. So you might be coming to a stop sign or coming to a stoplight, or you're leaving that stoplight and you're speeding up. You're changing your speed. How could you describe the speed of an object whose speed is changing? One way is to determine the object's average speed between where it starts and stops. The speed equation on the previous page can be used to calculate the average speed. Average speed is found by dividing the total distance traveled by the total time taken. For example, if you're taking any type of long road trip, you know that obviously on that road trip you're going to make several stops. You're going to stop at this gas station, you're going to stop at this wayside, you're going to stop and get something to eat. You're going to have to slow down and then speed back up when you're getting back on the highway. So the time you're traveling is going to change and vary based on how many stops that you're making or how many times you have to slow down, maybe if there's traffic or something else is going on. So your average speed is the total distance divided by the total time. That's just a calculation of average, how long it took you to take that trip. Instantaneous speed is a little bit different. Instantaneous speed is described, an object in motion can change speed many times as it speeds up or slows down. The speed of an object at one instant of time is the object's instantaneous speed. To understand the difference between average and instantaneous speed, think about walking to the library. If it takes you a half hour to walk 2 kilometers to the library, your average speed would be as follows. 2 kilometers divided by 0.5 is 4 kilometers per hour. However, you might not have been moving at the same speed throughout the entire trip. At a crosswalk, your instantaneous speed might have been 0 because you stopped to make sure that there was a way for you to walk across the street safely. If you raced across the street, your speed might have been 7 kilometers because you weren't walking, you were running, so your speed was actually greater than that average speed that was overall. So just because there's an average speed over the long period of time doesn't mean that that's the same speed that you traveled the entire time, right? It says here, if you were able to walk at a steady rate of 4 kilometers per hour during the entire trip, you would have moved at a constant speed. The average speed and the instantaneous speed or a constant speed are illustrated in figure 4, which is showing you that if you're speeding up and slowing down, your instantaneous speed is going to change, where average speed is calculated over the entire distance that you are traveling. Here's an example. Picture down below, the average speed symbol shows your Daytona 500, in which the NASCAR cars are going 500 miles, and however long it takes them to go 500 miles is the average speed that they were traveling. In the second picture, you've got a bike that's racing around a corner. Because he's going around that corner, he's probably slowing down and not going as fast as he possibly could in the race. On a straightaway, he goes a lot faster, so his instantaneous speed is going to be at that specific instant. Two very different examples, but both calculated the same way. Distance over time as your way of calculating that. How do we go about graphing this? Well, to graph this, we have to set up what's called a distance versus time graph. Let's read on page 286. You can represent the motion of an object with a distance time graph. For this type of graph, time is plotted on the horizontal axis. The horizontal axis here is going to be our x-axis. And the distance is plotted on the vertical axis, which is going to be our y-axis. Figure 5 shows the motion of two students who walked across a classroom plotted on a distance time graph. Distance time graphs and speed. A distance time graph can be used to compare the speeds of objects. Look at the graph shown in figure 5. According to the graph, after 1 second, student A traveled 1 meter. Her average speed during the first second is follows. 1 meter per 1 second is 1 meter per second. Student B, however, traveled only 0.5 meters in the first second. His average speed is 0.5 meters per second. So student A traveled faster than student B. Now compare the steepness of the lines on the graph in figure 5. The lines represent the motion of student A is steeper than the line of student B. A steeper line on the distance time graph represents a greater speed. If it's steeper, it's faster. If it's steeper, it's more speed. A steeper line on the distance time graph represents a greater speed. A horizontal line on the distance time graph represents no change in position that is occurring. In that case, the speed of the object is 0. If there's a horizontal line on a speed and time graph, that object isn't moving because the distance isn't changing. The time is going to continue going, but the distance isn't changing. So if it ever goes flat across the top, that means that there's not motion or movement that's happening. In this example, your x-axis again is your time, your y-axis is your distance. Number 2 says, how long did both students walk? Well, both students walked a total time of 2.5 seconds. Who has the fastest average speed? Well, that would be student A because it's steeper. Student B walked a little bit slower. Now, one of them went farther because they were walking faster in that same amount of time. This student was able to go 2.5 meters in 2.5 seconds because they walk 1 meter per second. This guy who's a slowpoke, student B, only walked about 1.25 meters in that same amount of time. So you can see the difference based on how steep that line is. A steeper line represents a greater speed. A horizontal line represents no change in position whatsoever. You might see that on your homework where the line goes up, showing that it's really fast and speedy, and then it plateaus, it goes really flat. That means that there's no distance that's happening, there's no change in position when that occurs. Look for that in your homework. Velocity. The motion of an object also depends on the direction in which the object is moving. The direction of an object's motion can be described with its velocity. The velocity of an object is the speed of the object and the direction of its motion. For example, if a car is moving west at a speed of 80 kilometers per hour, the car's velocity is 80 kilometers per hour west. The velocity of an object is sometimes represented by an arrow. The arrow points in the direction in which the object is moving. Figure 6 uses arrows to show the velocity of two hikers. The velocity of an object can change if the object's speed changes, its direction of motion changes, or they both change. For example, suppose a car is traveling at a speed of 40 kilometers per hour north and then turns left at an intersection and continues with a speed of 40 kilometers per hour. The speed of the car is constant at 40 kilometers per hour, but the velocity changes from 40 kilometers north to 40 kilometers west. Why can you say the velocity of a car changes as it comes to a stop at an intersection? Well, that's because it's not going at that constant speed. So the velocity of an object is the change in speed, and it also includes the direction in which that object is traveling. Now, here's why I showed you this picture of a baseball player named Aroldis Chapman, because he can throw a baseball 104 miles per hour. He's got a crazy velocity because that ball is moving in a specific direction. That's how it's described. In baseball terms, they call it velo, or velocity, in which that ball is moving. The velocity of an object is the speed of the object and the direction of its motion. That wraps up our study of what is motion. Today, again, we learned the definition of distance, speed, and velocity, and how to graph motion on our time and distance graph. Hopefully you can use that to help you complete your assignment. God's blessings.